This is Unit 8B, Firewalls and Network Separation, the second video covering the chapter in the CISSP book about telecommunication security. This specific unit, 8B, covers pages 628 to 657, which is Firewalls and Proxies. Firewalls, what do? How do they work? They protect internal systems from external threats by limiting traffic between the inside and outside. In the most general sense, in the sense they're usually adopted, this is what they do, is they protect your organization from the internet. Though for some organizations I've worked with, I might claim that a firewall protects the internet from them. They more generally connect two networks with different security policies. Think about it. The internet and your internal network have vastly different security policies in terms of what's allowed, who's allowed to do what, and what systems can be used for. Obviously, you need some sort of gatekeeper or control between these two areas with widely different policies to ensure that the policies of the internet don't affect the business value that's protected by your own internal policies. You can also use firewalls internally by enforcing the security policy of a network by constraining traffic to and from the internet. In typical use, it separates the networks into multiple zones. Each zone has its own security policy, its own set of risks, its own set of internal controls, its own purpose for existing. So with a firewall, what you're doing is not so much separating your internal network from your external or even different internal zones, but you may, as we'll see later, separate your connection to the internet into various zones having gradations of security and control, from the most exposed external servers to those servers that support them. Firewalls. This is a typical example of how a firewall may work in an organization. You've got the internet out here. You've got what we call a border router, which connects your organization to the IP address range of the internet from your own IP address range. The border router generally serves as a high-speed switching device for moving traffic between your internal network and the various routes in the internet. It defines your external presence to the internet, but sometimes a border router can perform security functions. It can do some very basic filtering of traffic to and from the internet. IP addresses, for example, that shouldn't exist on the internet may be blocked. You then have a firewall, one or two firewalls. In this case, you have dual firewalls. One firewall protects a server subnet called a demilitarized zone. These are servers that provide information to the outside world. So they need some level of protection by this firewall, but they also need to be exposed to internet traffic. You then, in this case, have a second firewall which protects the DMZ from the internal network, rather from the DMZ itself, because this isn't an entirely trusted network. It's somewhat exposed. You want your internal machines, your printers, your desktop machines to be even more isolated from the internet. In this example, we show two different physically discrete firewalls. It's entirely possible, in fact, it's a common practice, to have one firewall device with three or more interfaces on it. One interface is for the external facing, one is the DMZ, another one may be an internal trusted network. So this is just a conventional diagram. You may see cases where you've got two different firewall boxes cordoning off a DMZ with external facing servers. More commonly, you'll see one box with multiple interfaces. Types of firewalls. You have packet filters, working strictly at layer 3, stateful inspection, which is layer 3 plus some extra features looking at the traffic going through, proxies, which sit between the inside and outside and fully manage all traffic at all layers, what they call dynamic packet filtering in the book, which is basically a packet filter that allows you to set up ad hoc, as needed, open ports for specific communication, and then what the book calls a kernel proxy firewall, which is just a way of implementing the above in a computer system such that the functions exist within the kernel of the operating system. It's kind of a soup to nuts design of a firewall. Packet filters deal with traffic at the network layer. They don't care too much about traffic at the layers above. By the way, the reason they don't deal with data link and physical is because these only have local significance. Remember, the definition of data link is point to immediate point. So you're not filtering the internet, you're filtering the device sitting next to it if you do filtering at that level. They filter traffic based on IP level information like from to address, port requested, which isn't really layer 3 but is part of the IP packet, what protocol the upper layer uses, TCP, UDP, ICMP, and what physical interface, what plug on the box the traffic is seen at. They provide packet by packet control. A true packet filter has no knowledge of session status. It doesn't know the packets that traversed it before for that same session. And it can be, a typical example is a router configured to filter traffic, a very old style router that doesn't have session-based firewall functions, which most routers do. And it can be very fast, and it tends not to drop packets. So if you want very basic filtering and you need something that can handle a lot of traffic that's going very quickly, a lot of bandwidth, and you don't want packets dropped, this may be something you'd want to look at. Now, a stateful inspection is kind of a layer 3 packet filtering firewall. Plus, you start with a packet filter, then you add to it the ability to maintain state by remembering earlier packets in the session. If a packet number 1 that starts a session goes through the firewall, it creates an entry and saves it into what's called a state table. When packet 2 comes through, it compares that packet to what's in a state table and makes sure it's actually what's expected as the second packet in the session, and so forth. So it maintains a memory or a history of a session between a service on the outside and a client on the inside. So that way, if something happens that shouldn't happen based on its position within the session, something is out of order, it knows that and can react. It can prevent somebody from taking over a session by just forging packets because it remembers what the prior packets were, and it can say, wait a second, this didn't come from the right source. It also does selective analysis of the data contents, the higher level protocols, shown here by the arrows going up and down. It doesn't fully decode and interpret the higher level protocols, but it looks at selected patterns to make sure everything is consistent with how that higher level protocol is designed. It can look for things like obvious attacks. It can look for protocols that say pretend to be HTTP, but in fact aren't, and so on. They can be very fast. The content analysis, though, the selective analysis of data content, uses pattern matching. Attackers can defeat this by varying their attack signature and trying to evade detection. If the attacker knows what sort of firewall you're using, they can perhaps craft a packet that fakes out the analysis at the stateful level. A proxy firewall is a full-on client and server. It's a complete intermediary between the outside and inside. It proxies an application level service. It acts as both a client and a server. It allows you fine granularity of control. You can control traffic based on application functions, like FTP has get and put functions. An FTP proxy in a firewall can restrict these different functions separately. It can defend against application layer attacks. If somebody is trying to maliciously do something to fake out a web server or an FTP server, an application proxy in theory could detect this. It tends to be slower than other models because it has to completely decode the entire application protocol, and that just takes time. It takes CPU resources and memory. Proprietary protocols are problematic. If you're, for example, proxying something like Oracle and you're a firewall manufacturer, you have to jump through a lot of intellectual property loops to get Oracle to give you a copy of their code to incorporate in your firewall. And even then, it might be wrapped up or bundled in a black box that you can't completely deal with. It tends to be behind the curve for new services. New applications that are developed to be used on the internet may not have application proxies available for them for quite a while, and in that case you won't be able to effectively filter them. And in open application services are, of course, a point of attack. Now, dynamic packet filtering, this is something that the book deals with a bit. I assume the CISSP test covers it, but I've honestly, never heard anyone refer to this specifically as a type of firewall. I'm going to go over it anyway, though, because the concept is pretty interesting. It allows internal clients to set up communication on ports used ephemerally. Certain protocols will start out on an initial well-defined port and then say, okay, we've decided we want to use a service. Let's open arbitrary port X and continue on. A variety of FTP uses this, RPC may use this, etc. What it means is the client and the server are negotiating extra ports on the fly, which means you can't set up a firewall rule in advance. You have to have a firewall that's smart enough to decipher that sort of handshake, that sort of transaction where they agree to use a different port, and then dynamically set up packet filtering for that. Builds an access list on the fly to permit return traffic from the outside, and otherwise is pretty similar to a packet filter. Filters based on the IP level, from to IP address, port requested, protocol, and physical interface. The last one we'll go over as type of firewall is the kernel proxy. It looks an awful lot like an application layer proxy. It functions a lot, except that the entire communication stack is created for each, a new network stack is created for each communication. It evaluates the entire network stack to apply firewall rules, and it runs in kernel ring 0, the firewall kernel, for speed and efficiency. So you're not using a pre-existing device driver, TCP IP stack, etc. to perform your firewall filtering. You're generating this on the fly in ring 0 for each communication. This is a kernel proxy. Again, something covered in the book, something that should make some sense given our prior unit on hardware security, but honest to God, I haven't heard this mentioned in any of the material I've seen about firewalls outside of this. So keep this in mind, but outside of this class and perhaps the CISSP exam, you might not run into this too much. Now, architectures. We've talked about the types of firewall, and architecture is how you connect the firewall to your network, what goes on between here and there. Different types of architectures in order of increased complexity are dual-homed host, a single box with two interfaces, a screened host, a dual-home host that has a border router in front of it with the function of screening, providing some additional control over traffic, a screened subnet, which we covered earlier in the class in our basic intro, which is you have a firewall that has both an internal, external, as well as one or more DMZ zones that are screened subnet. And lastly, virtualized. The firewall exists as a virtual machine. Here are some examples. The dual home firewall we see here. There's the internet, there's the firewall, there's the inside. It's a very simple sort of architecture, no additional components, basically two networks inside and outside. You might see this, say, with a home router setup. The next one is the screened host. In this case, the border router applies certain rules to block certain types of malicious traffic. It's acting as a layer 3 packet filtering firewall here, and in the heavy lifting, the other layers of the OSI layer are covered by this firewall device here. And again, in this case, there's actually only two networks, the internet and the inside. Now, the next one we're going to go over is the screened subnet. We have the border router, and we have one or more firewalls, or rather one or more ports, because remember, these can be separate firewall devices. It can be one device with multiple interfaces. You've got a subnet here which has a server, and the point of that server is to provide services to the internet. You want that server to be protected. You don't want the internet being able to blow it away and compromise it full on, but you need to have some carefully constructed rules to allow it to talk in and out. You do not, however, need those rules to talk between the internet and the inside. You might need rules for the inside to talk to the server, though, so folks who are server admins or webmasters or whatever can update that server. Now, network address translation. We've talked about firewall types and architectures. It's a function of a lot of network devices can be done by firewalls, can be done by routers. You have what are called public versus private IP ranges. These are defined by the IETF. There are certain types of IP address ranges that are designed and intended not to be routed on the internet, but can be routed only internally within an organization. Usually an organization has a small number of publicly available, officially assigned outside public IP addresses, but you have a large pool of private addresses. You may only have one outside address and hundreds or thousands of private inside addresses. The problem is, how do you allow traffic to and from the internet to all of those private IPs when there are only a few public ones? The private IPs, remember, can't talk to the outside internet. Only the public ones can. You have to translate the private ones, the multitude of private ones, to a few public ones. Certain IP address ranges are reserved for private use. That's a private IP address, can't be routed. There are different types of translation. You have a one-to-one or fixed translation between public and private. You often see this where you have a web server that will have a single assigned private IP address that then gets translated to your organization's single public web address. You have dynamic translation where you've got a one-to-one but an arbitrary matching. You have a public address and it can match one of any, say, web servers that need to be viewed publicly. And then lastly, what we're most interested in is port address translation. You map a smaller pool of public addresses to a large number of private addresses, one-to-many arbitrary. You have many private, one or a small number of public, and the mapping is arbitrary. The way port address translation works is you have more internal addresses than external. Many internal addresses are translated to a single external address, and then the source port is used by the network address translation device, the firewall, the router, whatever, to distinguish the connection. You've got one external IP address, but you've got a different source port that it maps to the internal private IP address. This conserves public IP address spaces. You can get away with maybe one or two public IP addresses and use a large range of private ones. It also, by the way, is a security feature. It makes it difficult for external sources to directly initiate communication with internal hosts. Here's how it works here. You have the internet, which has public IP addresses. You've got a single public IP address here, 1, 2, 3, 4, 5, 6. This is your translation device, which can be a router or firewall. And then here's the internal addresses using this specially designated Internet Engineering Task Force private range. Anything within this range will not get routed on the internet. How does it translate? This device here has a translation table. For each inside device, it maps up the single external address with a specifically designated source port. So when the traffic comes back to port 2000, it knows that it goes to 10.0.0.0.1. If the traffic comes back to port 2001, 10.0.0.2, etc. So you're taking an IP address and assigning it to a port as a way of keeping track of it. And then on the return traffic, the PAT device translates this port and IP address combination to this internal port and routes it properly. Unified threat management. This is an interesting sort of device that you see a lot, particularly in the small enterprise and home enterprise, SOHO type of small office, home office environment. You have defenses at each layer in a single device. You've got your router, your firewall, your antivirus, and all that stuff wrapped up into a single box. This is really convenient. You can do all of your content filtering, intrusion detection. You can even set up a virtual private network for folks outside the office, and it's all one appliance that you just plug and play. Extraordinarily convenient, but it may present a single point of failure. You're buying a box from one vendor. If one of these components fail, you don't have any redundancy here. If there's a problem with the box and the entire appliance gets taken over by an attacker, you lose all of this protection. Doesn't happen too often, but something to keep in mind. It's convenient, especially for smaller enterprises. You know, if you're aware of the issues here and if you take care to manage it properly and update it, patch it, and be aware of any security vulnerabilities, it can be a very good thing to have. Proxy servers. We've talked about proxies in general as a type of firewall, but they also can serve as ways to control access between internal and external resources, in addition to just translating an application protocol. A forwarding proxy is inside out. You're on the inside of an organization and you want to go to an external site. You use a forwarding proxy to control the traffic from the inside going out to allow it to happen. A reverse proxy, on the other hand, is you are a member of your organization or you are an outside customer, outside user, and you need controlled access from the internet to an internal resource. Reverse proxies provide that access and attempt to secure that sort of access. And in open proxies, it's basically something that's out there, and it's a pass-through for general internet users to access public services. Oftentimes you'll hear to this referred in very negative ways as a potential security vulnerability. Oftentimes you'll run into open proxies as these kind of dodgy services that allow people inside of controlled networks to access websites they're not supposed to, bypassing filtering and so forth. But open proxies also have legitimate uses. Last point here we've got is a honeypot. It's a type of device that organizations may put on the outside. It's a lure intended to attract attackers. It's like a pot of honey attracts bears. A honeypot attracts hackers. It's a realistic looking but safe fake server with maybe a fake server environment. It's a simulated environment that no legitimate user should be able to see or should care about, but somebody who's doing an outside scan of your network may run into and may decide to try to attack. It is often used to gather threat information. Who is really trying to attack us? What are they trying to do? How sophisticated are they? And it's also sometimes designed cleverly to slow down real attackers. You have something that looks like a really wonderful target, but what it does is slowly bog down the attacker in increasing latency. There's one cool product called Tar Pit, because that's exactly what it does. Like the Ice Age mammals that got caught near La Brea, the tar pit type honeypot causes an attacker to just give up in frustration. And that's it for this chapter.